to demonstrate Young's double slit, I have a laser about 5 meters away projecting its beam onto the board. Now we did our theory for plane waves, but since the irradiance is fairly constant at the center of the beam, we can treat it as a plane wave. The light is going to be sent through two very close, very fine slits right in front of the laser. So let's go ahead and put in the slits, and you can see the pattern is different, and it even matches our prediction. So we predicted a sinusoidal curve, and that's what we have here: maximum, minimum, maximum, minimum, maximum, minimum. You can think of it as the cosine squared going from 0 to maximum, or you can think of it as a cosine that's been offset to where it also goes from 0 to maximum. But that's exactly what we got: dark, bright, dark, bright. We can kind of check the numbers according to this equation. So we say the maxima should occur at s, the distance times the wavelength over the spacing of the two slits, and that was m, it was an integer. So the spacing between the two is just s lambda over a, right? Because if it's 0 or 1 or 2 or 3, this is the integer, so just the spacing should be s lambda over a. So we can run some quick numbers. The separation is about 5 meters from here to where the laser is back there. The wavelength is about 0.6 times 10 to the minus 6 meters. It's in the red, so roughly 600 nanometers. And A, for these two slits, they're separated by 0.25 millimeters, right? So 0.25 times 10 to the minus third meters. So you put all those together and you get 5 times 0.6 is 3, and 3 over that is 4, that's 12. So you get about 12, and then you get times 10 to the minus 3 meters. That's what? That's about a centimeter. And if you look, sure enough, their spacing is about a centimeter. So we didn't do it in a precise way, but you can see we get about the right number. Now you may ask, why doesn't it go on forever, right? So this is just a cosine in terms of y, so it should go all the way up. There's no reason it should stop. Well, the reason it stops is eventually our approximation breaks down, right? We assumed small angles, so this formula is true for small angles. For larger angles, who knows what happens. Then you might say, now wait a minute, that's still a pretty small angle, right? If this thing's 5 meters away and I'm moving just a few centimeters, our small angle approximation doesn't break down. Something else is going on. Well, what else is going on is that these slits are not infinitely thin. It doesn't really throw its light evenly all the way around half a circle, right? That would take an infinitely thin slit. What we're really dealing with here is diffraction. So diffraction defines how the light will spread out when it goes through a finite slit, or a really thin slit for that matter. So that's part of the reason it goes down. And then you can actually see something else. It goes away and then it comes back. So let's turn the lights out and see what's really happening. All right, so now let's have a closer look at this. So we had our pattern and it goes away because of diffraction, but look at this, it goes to 0 and then it comes back. Now, this is pretty dim, so we're going to put one of the cameras really high sensitivity so you can really start to see it. And then, so we have it, it's back, and then it's gone again here. Look at that, it's gone, and then it comes back. And then it's gone again, and it comes back. So through this whole pattern, it's actually keeping the cosine that we just calculated. It actually does do the cosine way out, even to as long as the angles are small, but it's being modulated by this other function. Well, the other function is diffraction, and we'll be calculating that in the next learning sequence.